Et puis ensuite, il s'en est allé un peu plus au sud, à Aix-Marseille Université, à l'IRFE plus exactement, à travailler avec Stéphane Odizès et Thomas Lévesque sur les problèmes de vorticité, dont il va nous parler aujourd'hui. Et là, il est de retour en région parisienne, à sa plus grande joie, bien qu'il ait bien aimé Marseille aussi. Et il est alors là, c'est un peu compliqué, il est à l'école normale supérieure de Paris-Saclay, dans le centre Borelli, qui est la partie, le laboratoire de mathématiques de LNS Saclay, et il est à l'intérieur de LRC Meso, qui est une joint venture, comme on dit en français, entre donc le centre Borelli, l'NS et le CEA. Voilà. Et tu travailles sur des problèmes de Rayleigh-Taylor ou Faraday plutôt.
Et des sondes de Faraday.
Voilà. Donc,
problème de surface libre.
Voilà, bon, je te laisse la parole. Voilà.
Ok.
Merci.
Donc, je vais plutôt présenter en anglais. Mais c'est quand même sympa de m'accueillir. C'est vachement bien de pouvoir présenter dans les séminaires de métal. Ça fait longtemps que je ne le mets pas. Okay. So the work that I'm presenting today was done with Stefan and with Malibek, but also with Alisa Abraham, postdoc at the IRFE, and with Eduardo Duran, who defended his thesis a couple of years ago, and I'll present some of their work as well. So as the title says, we are interested on the instabilities of elongated vortices. So maybe we can start by that. So what is an elongated vortex? So I like showing this image around. So here you have a cloud of soft bubbles that is being illuminated with a light sheet, and you have a bird that's coming through. And what you see, if we follow the motion of the bubble, you get an idea of the motion of the fluid trained by the passage of the bird. Okay, so if you have this velocity field which characterizes the motion of particles inside this fluid, then you can get the vorticity field, which gives you a measure which tells you about their tendency to rotate, to swirl around themselves, and you can see these two very well-defined regions near the tips of the wings. All right. So what we call elongated vortex, from a certain point of view, is this concentration of vorticity into a tube-like structure, like the ones that are shown in this image, and each of these vortices is going to be characterized by a global quantity, which tells us how fast it is spinning, which is this circulation gamma. Okay. So one interesting thing we have in this system is this really interesting feedback between vorticity and velocity, where the vorticity field is going to create an induced velocity field, and at the same time, this velocity field is going to transport vorticity. So you have them directly coupled. Okay, so I'm going to show some examples of how you can you usually generate this type of vortices. So one way to do it is simply to push fluid through an orifice really fast, which is how we create smoke rings. I have an example here of a ring that is produced by Mount Etna. And we also have the vortices that are detached from a wing profile, like it's shown here. So you have this wing profile with some incoming flow, and depending on the operating conditions, you have some vorticity that detaches all along the profile that is going to roll up near the edges and create these concentrated tip vortices, which are advected downstream. Okay, so if we consider rotating machinery, you have the effect of this advection and the effect of rotation, and this is going to create this helical structures that we see here. And for this presentation, I'm going to focus on this type of structures. Okay, So you may be familiar with some of these structures. So on the left we have a vortex ring, which is characterized by a radius r and a size a. Next to it, we have a system of uniform helical vortices that are characterized by radius r, pitch h, and size a. And next to it, we have a system of helical pairs that have radius r, pitch h, separation distance d. And you can see that as we add additional ingredients, we have an increase in the complexity of the system. Okay, so if we consider that the size of the vortex, if the core size A is smaller than the other relevant scales on this problem, then we find ourselves in what is known as the advective regime, where all of these structures are going to move because of their induced velocity, but they do it in a way that you have a global translation in the case of the ring, and a global translation and a rotation of the helices, but the structure themselves are not going to change shape. So this is what we call an steady solution. All right. So these structures may be steady, but it doesn't mean that they're stable, in particular with respect to external perturbations. So the stability of vortices has been the subject of numerous work, but globally they can be grouped in two kinds. You have the short wave instabilities and the long wave instabilities. In short wave instabilities, you have the wavelength of the perturbations is comparable to the core size, and the instability itself is caused by is triggered by the internal deformation of the core, like in the case of the elliptical and the curvature instabilities that we can see here. But for this presentation, we're going to focus on the second kind, where long wave instabilities, where the wavelength is large relative to the core size. So what we observe is going to be a global displacement of the vortices, like we can see in this image for the case of an helical vortex. And this is interesting because we'll be able to characterize these instabilities using the filament approach. Okay, so maybe we can start with this. We know that helical vortices are unstable with respect to long wave perturbations. So for this geometry, is going to be convenient to express everything in terms of this azimuthal wave number k, where value k equals 1 corresponds to 1 turn of the helix, right? So if we express the growth rates of the instability as function of the growth rate, we for a typical case we get a diagram like this that is characterized by local maximums in the growth rate for multiples of k equals 1/2, 3/2, 5/2, and so on. Another feature is that the maximum growth rate is going to scale with the distance h square, where h is the separation between neighboring vortices. All right, so if we look at the displacement induced by the most unstable modes, we get these three images, and we can see that the most unstable modes are going to amplify displacements that are out of phase between consecutive vortices, between consecutive loops. That means that this filament is going to move in one direction, the other one is moving in the opposite direction, and they're getting closer together. Right, so this is what we call a local pairing event. And for the case of mode k equals 1/2, all right, so the pairing is best seen on this type of diagram if we unroll the helix into the developed plane, and you can see how they are getting closer at a specific location. And in the case of mode k equals 1/2, what you get is one pairing event every 2 rotations of the helix. In the case of k equals 3.5, we have 3 pairing events every 2 rotations, 5 events every 2 rotations, and so on. But they all have the same general mechanism. Okay, so now if we take a look at the system of 3 interlaced helices, you get a similar picture. But here we're getting 3 branches instead of 1, where one of these branches, the motion of the helices is coordinated. They all move in the same direction, whereas in the other 2 they are phase shifted by a value 2 pi over 3. Nevertheless, the mechanism behind these instabilities is the same. So we have this amplification of displacements that are going to create this local pairings, like we can see here and here. All right. So we also have a special case in addition to the local pairing modes. We have the modes for exhibit at uniform deformation, and they're getting closer together. So this is what we call global pairing. Okay. So this is really nice, and it's interesting, but we would like to show that this is also relevant for different applications. So in this particular case, the 3-helix configuration is interesting for the wind turbine community, since most wind turbines have this 3-bladed rotor arrangement, like we can see here. But in particular, this is going to be interesting for wind farms, like the one that is shown in this picture, where you can see how the wake that is produced by one turbine arrives into the one that is located downstream, and this is going to have a negative effect on the performance, right? So and this is really problematic. In some cases, depending on the atmospheric conditions, these wakes may extend for up to 50 kilometers long. So the presence of the wake really limits the amount of energy that you can produce in a wind farm. Okay, so this means that we have this motivation to look at different strategies to accelerate the breakdown of the wake. And some of the ideas that people have been floating around in the community to use is to use different devices to trigger the hydrodynamic instabilities that we just show for the 3-helix system, and see if that way we can accelerate the breakdown of the wake. We have different ways to do this. So for instance, here, the authors propose adding a flap with an actuator. So this is going to move as to excite a specific frequency, and the idea is to tune in this frequency with the frequency of the stability. Another alternative is to change the yaw, which is the relative orientation of the wind turbine with respect to the incoming flow. So they want to move the turbine like this, also to excite this instability. And but you can also do other things like change the pitching, which is the angle of attack of the blade in a dynamic way. All of this, they work with the same premise. But you can imagine that systems like this are really sophisticated. They involve some degree of mechanical complexity, and you may also wonder what can we do with the ones that are already existing. So how to find a solution that can be retrofitted to existing wind turbine. So we see a motivation to find more simple ways to trigger these instabilities through different forms of passive control. So for instance, we could think of adding something at the end of an existing rotor to add an asymmetry to the blade and use this to excite the system. Or we can add another additive to change altogether the geometry of the wake. So these are some of the ideas that we've been developing at the airframe. Right, and today I'm going to focus on this type of strategies. Okay, so this is done in 2 parts. We have some experimental measurements taken at the water channel at the IRFE. And we also have a second part, which is focus on using these results to validate engineering models. So first, I'm going to present the experiments that are done at the IRFE. So this is a little bit odd for me because I'm not really an experimentalist, but I can gloss over the details. So basically what you have is a recirculating water channel with some free string velocity. Inside we have a rotor that is suspended on a shaft that is rotating at a velocity of with a frequency of about 3 hertz. And we are able to change the rotor and test different configurations. So in this case, we are using a three-bladed rotor with that is 9 centimeters in radius, that is 3D printed, and is based on a NACA 2414 profile. And the idea about this design is to have a more or less constant circulation profile to get some really clean results. Okay, so in this setup, we are going to do a couple of things. We're going to test a configuration with a symmetric rotor, and then we are going to test two configurations which are going to excite these unstable modes. The first one that we're going to try, we're going to change one of the blades of the rotor and use a blade that is a little bit longer. A little bit longer means a couple %, as to induce an asymmetry. And in the second configuration, we are going to change the rotation rate. We're going to introduce small modulation as to excite one of the other modes. All right. So basically, what we do, I'm going to start by showing the base results for a symmetric rotor. So we can do a couple different things with this setup, but what we use the most is fluorescent dye visualization, in which we add some fluorescent dye at the tips of the rotor, and we illuminate this with a LED light, and this allows us to get these really nice images of the wake. Okay, so I'll have to specify that we only use one color in the experiments. We are using fluorescent. So we only get the green light, but to be able to show this a little bit better, Thomas took the work to add colors by hand, which is a lot of work. Okay. So if we look at the baseline configuration, what we are going to see is the rotor here. The presence of the rotor is going to induce a small expansion in the radial direction, but not too much. And the system is going to quickly converge to a system with uniform helices, like the ones that we saw earlier. There are other things that we can see. For instance, it's remarkable how persistent the wake is. The filaments remain pretty coherent until the end of the field of view, and just near the end they start to break down. This is by the shape of it, we believe this is related to shortwave instabilities, not really the ones that we are interested in. So we tune the parameters of the experiment precisely to delay the presence of these instabilities. Right. So now we can see how this changes when we use the symmetric rotor. You can see the structure of the wake changes a lot. It's also very consistent. So the structure itself is not going to change that much. In this case, what we're going to see is a uniform expansion of one of the vortices. One of the vortices goes outside, the other two go inwards a little bit, and this is going to induce a velocity difference, so that eventually the vortices are going to trade places. This is what is usually called leapfrogging. And then they return to another position. So in this case, you have this vortices continuously trading places. You have the blue outside, green and yellow inside, and then you have green outside, blue and yellow inside, and so on. Yes, are the same. Actually, no, they're not shorter. They're just the same. So the system was designed like this. We have a bolt in the rotor. That way you can unbolt one of the blades and put another. And that's how we test the different configurations. It's slightly longer, yes. The profile, it's roughly the same. And the circulation of the tip vortex is also roughly the same. It doesn't change that much. This was done on purpose, because that way we can isolate the effects and we can compare different models. So I have to mention as well that the rotors were 3D printed. That way we were able to test different blade profiles really fast. So this is something that the engineers at the UK know how to do really well. Okay. So if your blade is slightly longer, you have this change in the structure, and this is interesting because we have a couple things to mention. For instance, when the vortices are trading places, this is also the moment where they're also very close to one another, and we believe this is going to induce or at least accelerate some of the shortwave instabilities that appear later. And we can see that some of the vortices actually seem to break down a little bit faster. So this seems like one option. Now we can look at the other way to trigger the instability is to add a small modulation at the rotation rate. So in this case, a couple %. And the frequency of this modulation is tuned to trigger a specific frequency. In this case, it's tuned to trigger the mode k equals 1/2, 1/2, 1 and 1/2, 3/2, which is the maximum, which is the largest, the most unstable mode that we can excite with this configuration. Okay, so what happens here is a little bit more complicated. You get some traces of the unstable modes. So you have these local pairings that can be seen, for instance, here. But you also have like a lot more complicated things like loopy things and vortices that are rolling into themselves, trading places. Things that are a little bit complicated, and that people usually tend to explain by saying that there is turbulence involved, and this is some disorganized motion induced by turbulence. The idea is to show that this is not the case. Is more these motions can be perfectly explained by the nonlinear dynamics of the system. Nevertheless, you can see this configuration is quite complicated from a geometric point of view. So there's going to be a limit to what we can do with the experiment. All right, so there's a couple more things that we can measure. So if we illuminate, we take a laser sheet to illuminate the midplane, we can track the trajectories of the vortices, and from the trajectories of the vortices, we can obtain a really good estimate of the exponential growth rate to verify that we are indeed exciting the right instability. Okay. And when we do that, we observe a really good agreement with the linear stability theory. This is one of the main results from the experiments. However, you can see that there's a lot more information in this system that may be too difficult to measure. So the idea is, can we get some additional information? using a simple model. All right. And well, when we say simple model, we really mean simple, because the idea is to use this in engineering applications. So we need something that's really easy to use. So this means that instead of using a full description in space, like considering Navier-Stokes or this type of equations, we're going to look for a simplified description. We're using a filament model. So in this type of models, what we do is that we consider that all the vorticity is concentrated along these thin filaments, which behave as one-dimensional curves embedded in space, so that the filament can be described by the position of so that the vortex can be described by the position of this filament and by some model of what's going on inside the vortex. In our case, we use Gaussian vortex, like around OCM. All right. So I'm just going to write some of the assumptions and simplifications. So we consider that these filaments are illicit. So we are working with an ideal fluid. They are force-free and they are affected by the local velocity flow, which is composed from the velocity that is induced by the vortices, evaluated using Biot-Savart, and by some external velocity field. All right. So we took a numeric approach. So these filaments are going to be discretized into a number of straight segments, like we can see here. And to compute the induced velocity, to deal with the singularity in Biot-Savart, we're going to cheat a little bit, and we're going to split the induced velocity into a local and a non-local part, where the non-local part is computed from the straight segments using Biot-Savart, and the local part is obtained by fitting an arc of circle that passes through neighboring points, and replace the contributions by the exact solution for an arc of circle. All right. So I have to mention two things. That the only place where the core size and the core model is going to intervene is going to be in the local parts through the core size, but also through this parameter delta, which depends on the distribution of vorticity that you have. Okay. Another element that we are considering is that we allow the filaments to stretch. That is, you have a local strain field. These filaments may stretch or compress. And we do it in a way that the total vorticity of the system is preserved, which in practice means that the material volume of these vortices is also preserved. So if you have some stretching, the core size is adapted accordingly. Okay. For rotor configurations, we have this. It is often convenient to express everything in terms of the Lagrangian coordinates c and theta, where c is the angle of the rotor at a given time, and theta corresponds to the difference, so the angular position of some vortex particle at the present time, and its position at the time where the vortex was emitted from the blade. So it is related to the age of the vortex. So in practical terms, what this means is that the variable c is going to be used as a proxy of time, and the variable theta is a proxy of space, and we can obtain our dynamical equation in this way. So this system is completed by a set of boundary conditions. So depending on the boundary conditions, we may get different systems. So if you consider periodic conditions, we get a system of infinite helices. But we may also prescribe the positions of the vortices at one point and have them to match a uniform solution in the far field, which is going to be useful to take into account the presence of the rotor. Okay. So this is a very classical model, And one of the questions you may be asking is, why use this instead of something more recent? Why not DNS? Why not LES? Well, the thing is that there's a couple of things that we can do with this model that are really hard to get with other formulations. So I'm going to start with this one. So first, we can, if we search for solutions with the time dependency 0, we can search for stationary solutions. And like was done by Eduardo and Stefan, for the case of two-bladed rotors, they were able to characterize the wake for all regimes, for all wind turbine and helicopter regimes. And in these cases, the whole system is characterized only by the geometry of the planes. This is something that you can't really do, or it is very difficult to do otherwise. Okay, so if you use this to get the stationary solution, we can then look at the stability of this stationary solution. So we introduce a small perturbation and linearize around the solutions to get a system like this, and we can get back the instability of these more geometrically complex configurations where you had no previous prediction. Okay, so this was also done by Eduardo and Stefan. So what they did is they took one of these configurations, they introduced a small perturbation near the rotor plane as a direct impulse, and they looked how that perturbation propagated downstream. They were able to show that in most cases, since the perturbation is quickly propagated downstream towards the uniform helices, the stability properties that you are going to get at the end correspond more or less to those of the helices. So that sort of reinforces this idea of studying this uniform configuration. Okay, so we have stationary solutions, linear stability, and of course, if you have that, what you would like to do is to look at the nonlinear dynamics, and this is what it's going to be interesting for us, because most of the interesting stuff that we saw from the experiments actually happens in the nonlinear region. So we're going to focus on this part. We're going to introduce a small perturbation to the solution, and we are going to see how that behaves. And the idea is to choose a perturbation that sort of mimics the ones that we have in the experiment. All right. So we are going to do the same. So first, we're going to present the baseline configuration. This is what you would get if you had asymmetric rotor. Right, I'm going to play this. So the structure doesn't change, but I added the rotation of the blades to illustrate what you would see in the experiment. So you get similar type of behavior, radial expansion, uniform system, etc. Now we are going to see what happens when we introduce an asymmetry. So we're going to take this configuration, we introduce radial asymmetry, and we're going to see how this propagates back. All right, so we start with the baseline configuration. Here you start to see propagation instability. Then you have leapfrogging, and what you get is something that's really similar to what we see in the experiments. If we follow the evolution of the perturbation as function of space, we are able to recover the exponential regime really well, and the transition towards nonlinearity. Yes, so the rotor is here, and the perturbation is propagating from left to right. Yes, but this expansion, it depends on the operating conditions. So in most cases, this expansion is small with respect to the radius of the rotor. It's about 5–10% in this case. So it's there, but it's not easy to see visually, at least. It's measured, but it's not easy to see. Okay, so we are kind of happy with this, but then, well, we had the question, can we do something simpler? So the idea is we're going to remove some of we're going to remove some of the elements and reduce it to the really basic elements. So if we take uniform helix and we unroll it on this developed plane, what we see is that the helix, if you look at the helix from this angle, what you're going to see is sort of an array of periodic vortices. So we're going to approximate the dynamics by looking at these the model with based on point vortices. We're going to add a small perturbation, and we are going to see how this evolves. So I have an example here. So you have the trajectories of the three vortices in each color, and you can see how they are moving. And what we're going to do next, we're going to take this evolution, and we're going to add back this perturbation with a rotation rate and an actual velocity to reconstruct back the helical system, and we get this type of structure. So what we can see is that the leapfrogging and a lot of the features that we saw earlier can be explained only by the nonlinear dynamics of a very simple point vortex system. So you have no curvature, you have no rotor, you have no anything. Everything is of a smaller order than the nonlinear dynamics of this system. Okay. So we made some comparisons with the experiments. So in this case, it's rather simple because you have this leapfrogging event that is going to facilitate the comparison. So we measure the distance between the rotor to the leapfrogging. In the case of a two-bladed rotor and in the case of a three-bladed rotor, and we get really similar results. You can also get the feeling that the shape is also very similar. But we also get a decent quantitative agreement. So if we measure the distance to leapfrogging as function of the tip speed ratio or as function of the amplitude of the perturbations, we get a decent agreement. I mean, all things considered, we get a really good agreement between the experiment and the vortex model. Okay, so this concerns the leapfrogging distance, but it also applies to the trajectories of the vortices themselves. So here we have the trajectories of the model in continuous lines and the trajectories from the experiment in dashed lines, and you can see how they actually they actually follow one another. We have a rather decent agreement. Okay. Now this is fine, but with the point vortex model, we can only get one type of unstable mode. So we are going to go to the next level. We're going to replace the point vortex by a system of uniform helices in a way that we can introduce a spatially periodic perturbation. We're going to follow the evolution, the nonlinear temporal evolution of this perturbation, and then we're going to use this to get back to reconstruct the helical system. So it's the same principle as before. We have an example of the reconstructed helical system on top, a view in the developed plane at the bottom, and you can really start to see some of the loops and wiggles that we saw earlier. We're going to be able to identify some other characteristic features. So in this case, there seems to be a moment where the vortex becomes more or less vertical, right? So we are going to use this as a reference point. This is better seen in this image. And we also have points where the vortices are trading places. So we have this type of flip turbine as well. All right, so we're going to focus first on this distance to a vertical feature. Okay. We can use these results and compare it with the experiments. The experiments are on top. The results from the model are on the bottom. We have a really decent agreement between the two. You have this sort of straightening, you have this looping, and we have all these features that are seen here that people use to justify by saying that there is some sort of external flow field that generates them. In this case, we can show that these features are indeed generated by the nonlinear dynamics. So if we're happy with this, and we consider that the model can be used as a proxy for the experiments, what we can do is try to get some additional information out of the model. So in this case, at the bottom, we are showing in color the minimum distance between two neighbors to show how two vortices are getting closer to one another in the far field, and how this is going to affect the stability of the wave. So this is one of the quantities that we can extract from the model. All right. So if I return to the distance to this vertical feature, what is different in this case is that the distance to the vertical feature is actually not fixed. It's going to change in time with a period that is given by the unstable mode, right? So basically, the distance to the vertical feature is going to oscillate between a minima and a maxima with a period that is given by the unstable mode. And if we measure the same quantity on the experiments, we get sort of the same tendency. The comparison is a little bit difficult to make because we have the limitations of the experiment, but the idea is more or less there. Okay. We can also look how this distance changes with respect to the amplitude of the initial perturbation, and we get this sort of exponential this log law, and we can tie back the distance to the vertical feature to the exponential growth rate. We can do this in the model and the experiments, and we get more or less decent agreement. Okay, so this covers the basic of our results. So I'm going to leave the conclusions here. Basically, we presented a more general approach to stability analysis that can be generalized to different geometries. And we are able to show this interest in studying the nonlinear regime. We proposed a simplified model that takes into account that are able to get get a really good agreement with the experiments, and show that we may infer some additional quantities that are really hard to measure by using this model. All right, and I'm going to stop here. And if you have any questions, I'll be happy to answer them.
Thank you, Andre.
It's not really a question, but rather a comment, just to start the debate. It's very difficult to define turbulence. I think the subject of many controversies over the past 100 years.
Yeah.
But in a way, one way to define fully developed turbulence is that involves algorithm of modular and complex interaction of vortical structures.
Yeah.
And in the case that we are showing here, even if there is no vorticity outside of the filament, you could still argue somehow that there is complex interaction between vortical structures. So you could say, in fact, that just the deformation of the filament
Yes, I get the idea. Maybe what I should stress is that this motion is deterministic instead of random. That is something that would, that doesn't need me to define turbulence, because I don't like, it's a risk to define turbulence during a presentation. Yes, so I would rather not do that. But this is a purely nonlinear dynamics of a deterministic system, and this is actually kind of interesting. It shows that we should look into these questions a little bit more.
Another question or comment? Well, I make a comment on Stefan's comment. That's a sort of turbulence thing, walls and so on. Here the point is, it's not really turbulence, because the feature that is very astonishing here is that the vortices stay coherent. Each one produced at the blade. There is no reconnection whatsoever. And you expect, and so maybe if you put some small perturbation, well, you mentioned the core size instability, then maybe you get turbulence. So here is what is incredible on that picture is that there is no reconnection, though it's very entangled.
Yeah.
If you wait longer?
Yes, if you wait, yes, but even at that point, you would expect something to happen, some kind of reconnection. And if you put, yeah.
No, please go ahead.
And if you put some long wavelength displacement instability, as is done here, but you had also some very small core size instability, you get turbulence right away, which is, I think, very interesting feature.
Yeah. So regarding why can't we look longer, we are limited by two things: by the size of the water channel, but also because of the fluorescent dye is washing. So at some point, it's really hard to get clean measurement. In the models, you can continue as long as you want. And what's interesting here is that if you continue, you're going to get the same type of structures, but they're going to be a little amplified. So in these structures, what you get, if you look at the structures, we have some parts of the filament that become more straight, and others that are bending. And as you go downstream, the straight part is a little bit longer, and the bending is a little bit more severe, so you get this sort of corner. So we really expect that the vortex is going to break or something like that. Physics doesn't like sharp corners. So.
Thank you. I can say that's a very nice talk. Thank you very much.
Thank you.
No questions? I have one left. You mentioned the beginning of your talk, Wang. The flap with the...
Yes.
So this has been tried on real scale wind turbines?
Not that I know. It's been
yes.
tried on models, on LES simulations.
And on the real experiments, or even not small scale experiments?
Not that we know.
Okay.
I can imagine it's very tricky to do it at lab scale because it's going to be very small. And large scale is going to be expensive.
Yes.
So the idea precisely is to avoid this type of complicated systems because it's going to be hard to get. So to come back to the matter of small scale instability, that is precisely what Thomas is doing right now. So he's adding a grid before to the water channel to introduce some turbulence to the system, to show that the vortices are going to break a little bit faster, and that is going to happen just behind these regions where the vortices get a little bit closer. Yes, okay. So that is something that the people at IRFE are doing right now. I don't know if they have the results already, but I think it's very logical.
Again, and let's thank you again. So Andres is here for the day if you want to talk with him. feel free.